Okay. Now streaming. With a much needed cup of tea, I'm ready. So, as you can see on the screen, oh good god, we're going to go into infinities here. As you can see on the screen, people were interested in seeing how I wrote a program whereby I managed to evolve a walking horse, which is quite fun. Can everybody hear me? Am I actually audible? Give me a cheer in the chat if I am. Ooh, that's good. Right. Okay, so I'm going to be using something a bit new today that I've never used before, and it is called where the heck are we? It is called Quicksilver, which is a cargo or rust crate, which it's a rust crate that allows us to write web apps. So I'm going to try making this as a web app, mainly because I want to learn how to use it, but also it might be quite cool to try this thing out on the web. So first of all, I'm going to do the customary create a new Rust project. Let's call it, I don't know, Darwin, how's that? I'm sure Charles himself would be very proud of this magnificent creation to be. Right, first off I got to install something that lets me deploy a cargo project to the web. So just a bit of screwing around with commands, shouldn't take too long. Right, so our goal is to first of all build a very simple physics system which we're going to use to simulate our creatures, and then afterwards we're going to evaluate them afterwards and try to evolve them. So while we wait for this to install or build or whatever the hell it's doing, I'm going to start work on that physics system. So this is going to be a very simple physics system. There's going to be no complication to it. It's not even going to be accurate according to Newtonian mechanics, but what it's going to let us do is connect several points together. Oh damn, that tea's hot. And make them move in interesting ways. So a good first place to start is to create a struct called, let's call it point, okay? And I'm going to use a crate that I use quite often as a third-party crate. It's called Vec, and it basically just gives us a bunch of types that we can use for working with vector values. So things like 3-dimensional or 2-dimensional vectors. It's pretty useful, as you might expect. So first off, our point in space is going to have a position. So let's give it one. So this type here is a vec2, which means it's a 2-dimensional vector. In terms of how this is actually represented in code, it looks something like this. It's just two floating point numbers that correspond to our x and y position. And now we're going to create something called, let's call it, I don't know, a body. So our body is going to be composed of points. So each body is going to be one of our creatures that we want to evolve in some way. And so to give it a load of points, we're going to give it a vector, because vectors are extremely useful in so many circumstances. It's going to have a vector of points. I should zoom in actually. Can everybody see this all right? Hope I'm not doing things too small. Right, so our body has a vector of points, and on it we are going to implement a function that lets us create a new body. And it's going to have no points at first, so just an empty vector. Another important thing that these points need is a velocity. Now, velocity of course lets us make a creature that behaves in a dynamic way, moves about, etc. We could give it a mass, but since all points are going to have the same mass, we don't really need to care about that. So we're going to give our point a function as well. Zoom out, it's a bit too big. Going to give our point function called tick. Now, tick is just going to update our point in space, so that means it's going to apply its own velocity to its position. So that looks like this: self.pos plus equals vel. So what this means is that if we call tick, let's say 60 times a second, it should move across the screen, assuming that there's a velocity that's not zero. We're also going to apply the same to the body. We're going to give it a function called tick, and we're going to make it tick all of the points in the body. So for point in self.points, we're going to borrow it mutably like this, because we want to mutate the points, change them. Point.tick. There we go, perfect. So we have a bunch of detached points, which is all very well and good, but we want a way of allowing them to be joined together, okay? Because our creature isn't going to be much use if it doesn't have any bones that go between its joints and allow it to move around. Tea break. So we're going to represent each joint as a tuple containing the indices of the 2 points that join together, okay? And it's going to contain one more thing, which is the length that's meant to be between them, okay? We can use this to move the points apart if they get a little too close together, or move them closer if they get a little too far apart. So yeah. So after we've ticked each of the points, we're going to go through this vector of joints, and we're going to update those points for each joint and make them move about in a sort of elastic type way. So for self.joints, notice we're not taking a mutable reference because we're not trying to change the joint itself, we're only trying to change the points that it's attached to. Yes, that's tea. Nice tea, I might add. Yeah, that's right. Aren't you envious? I'm drinking it out of a periodic table mug. Best Christmas present. So dist here is our distance that we aim to have between both joints, and A and B are the indices of the points themselves, okay? So now we're going to find each point according to their indices. So for example, we're going to find their position. We do this because Rust can be a little insecure about its borrowing rules. We don't want to make the compiler upset. So we have the 2 positions. So now what we want to do is, if they are closer than the desired distance, we push them apart. And if they are further than the desired distance, we push them together. So we do this by first measuring the distance between them. We can do that with a pos minus b pos, and then we apply a method called magnitude, which is a method on the vector type that we started using, and that will give us the magnitude of the vector between them, i.e. the distance between them. So, and now we need to compare that with the distance we desire. So let's call this r_dist for relative distance, and if this value is above 0, then the points are too far apart. If it's below 0, then they're too close together. So now we want to apply a change in velocity to the points according to whether r_dist is above or below 0. I should turn off my boiler because it's quite loud. There we go. Okay. Ooh, nice try. No, this is the best tea. Is that foul there? Yeah. You Germans, I think you're jealous of our tea. It's the only real answer that makes sense. Okay, so now what we want to do is we want to find the velocity vector that points from A to B. So in fact what I'm going to do is I'm going to bring up a program to just illustrate what I mean. Let's bring up another window. Okay, and we're back. It seems like my streaming software really didn't like me doing that and decided to freeze. So, to illustrate what I'm talking about, we have 2 points, A and B. Yes, I'm drawing these with a touchpad. I'm that cool. So, we want to find the vector from A to B that moves us closer to it. So the way we do that is to take A to B is equal to B minus A. Quite simple. But now we want to do something else. We want to do we? Yes, we do. We want to normalize it. Now, normalizing will set its length to be equal to 1. So, as we said before, if r_dist is greater, or rather, if the distance between points is greater than the desired point, then r_dist is going to be above 0. In this case, we want to move the points closer together, so we want to move A in the direction of A to B. So we're going to do this now. We're going to do self.points A.vel plus equals, so we're going to add something to the velocity, A to B times r_dist, and then we're also going to add a little factor on the end to make sure the physics doesn't go crazy. And now we do the same with point B, except this time we're subtracting that vector because we want to make it move in the opposite direction, which is towards A. So that's all fairly simple. And now the next thing to do, oh, cargo web is installed, right. Now we've got to work out how to, oh, I just realised I had that on the screen all along. I'll get rid of it now. There we go. So I'm just changing the velocity vectors according to A to B, which is our normalised vector between them. So now I just have to work out how to use Quicksilver. Let's give that a go. I also need to plug in my charger. Right. Bunch of things that we need from Quicksilver. Note, I've not tried this before, so it could fall down around our ears, but let's hope not. At the moment I'm basically just copying an example on the Quicksilver project's homepage. Right, so now we're going to create a struct for our program. Let's call it world. World will contain all of our bodies, all of our creatures, like so. Now we do a little bit of Quicksilver stuff in order to make it work. No. So we start off with an empty vector. Now this is the routine we use to draw everything on the screen, so we're going to want to draw lines between all of our points. Let's hope this works. First of all, we're not going to draw anything other than a white screen. Just to test it, we're going to return OK. Let's assume there's a success. Right, now the Quicksilver code to get everything started is means. So, according to Quicksilver, we can use the cargo web start command and it should work. Let's see what this does. Oh, it's downloading something. That's fun. Hopefully this doesn't take too long. In the meantime, I'll show you what I've been writing for Global Game Jam 2019. Our team is working on a project to create sort of a 3D looking game, but without using a 3D engine. This is an engine that's got a lot more in common with the original Doom's engine. It renders things in the same way. It actually uses ray marching, column-based ray marching, as in the original Doom and things like Wolfenstein. Yeah, it's nowhere near ready yet because we've only had a few hours to work on it. And eventually it's going to be sort of the type of game where you need to defend your house while keeping out hordes of zombies or whatever. Yeah. Right. Come on. Hopefully it's getting close now. For you people still watching the stream, well done, you're very dedicated, since we're just watching things compile now. Rust is great, but damn does it take some time to compile things. Oh, you've got the medicine, have you? Right, God bloody hell. This really is taking its time. Right, so here's the plan. Once we have our window displaying, we're going to start to draw some lines between all of the points, in all of the joints, in all of the bodies in the world. Now that's a mouthful. I'm just killing time here. Joints. Well played, well played. You know, I read that as aye joints. Is that the noise that you Canadians make in your free time then? Right. Wow, Quicksilver has quite a few dependencies. Still, if this works, I should be able to host the program on a website and then anyone can have a go at screwing around with creating their own evolved creatures. Not that there don't already exist about 100 different games that do exactly the same thing, but oh well, it's fun to do it ourselves. Animations with the new engine. What do you mean by save them? At the moment, animations are implemented using a trait system in the code. So if you go into put the location in chat. Pretty sure this is it. If you go to that location, you can see how you define an animation. You can create a file just like that one, link to it from the mod.rs file in the same place. You can create your own new animation. In terms of actually placing those animations in game, it's probably best to send the code to me, and then I can look at integrating it into the engine through the proper means. Ah, my god. Still compiling, which is why my laptop is running like a legless pig. I'll also check out in the function called maintain, I believe. Ooh, yeah, it is quite a few dependencies, but hopefully as Rust gets better, it'll get faster. But oh, okay, yay, we've got to compiling my code, and of course my code is full of errors. Cannot find value vel in this scope. Oh yep, that's because I did a derp and didn't do self.vel. Missing joints. Oh well. Yeah, it's both of us then. At the moment, let's just create an empty group of joints. Oh, joints, not points. It's quite annoying, but they rhyme. No method names normalized. Oh, whoops. It's because we should have done bpos and a pos, not b and a. This match type needs a result. Oh, we need an OK around that, since it creates a result. Here we go. So, one last error. Cannot move out of borrowed context. Well, that's because we need to borrow that vector. Oh yay! More errors. Okay, so this is all because when we borrow this vector, it gives us references to all of the things in here, which means that A is now a reference to a U size as defined up here, as is B. So the simple way to solve this is just to dereference them here. Quite straightforward. This is a creaky chair, that's for sure. Let's check chat again. Gone down to 3 people now, I don't blame you. This is quite boring at the moment. Well, if we load localhost, let me just no, wrong one. Just switch back to our web browser. You can see we have a blank screen. Woohoo! That was worth it, wasn't it? So that's just because we've drawn a white colour to the screen. Let's try red just to see whether it works. Oh wow, it's automatically recompiling. Isn't that clever? all I need to do was to save the file. If we refresh, we have red. That's really good news. Things are working. Okay, now the next job. Drawing some lines. So we're going to go for every body in self.bodies, for every joint in body.joints. Yeah, we have loops inside loops here. So each joint actually looks like this, A, B, and then we don't care about the dist, so we put an underscore here just to ignore it. So we do pos, or A pos, just like before actually. I'm going to copy and paste this code here. Actually, is this the best way of doing it? No, actually, I'm going to comment this out for the moment. Before drawing joints, we're going to draw points. That sounds like it should be a punchline, but it's really not. Right, okay, so for each one, let's try drawing a circle. I need to import circle at the top. Right, window.draw. Are you ready for this magic? Circle, new. Right. Where is it going to be? Well, it's going to be at the location of point.pos.x. What are the coordinates it uses? I don't know, let's work it out when it produces an error. Point.pos.y. Now, how big do we want to make this circle? Let's make it 20 pixels wide. Nice round number. And colour, well, what colour do we want? Let's go for green. Let's just change this to colour like black for now. Right, hopefully this all works, and there doesn't seem to be any errors. That's good. So let's refresh the page. And as expected, there is absolutely nothing on the screen because we've not created any points yet. So let's do that. So let's create a body first. Let body equals body. How do we construct it? I'm going to make it mutable because we're going to add some points to it. Body dot points dot push point at what position? Let's go 32, 32, and let's create another point at 128, 128. Yeah, we need that to be an F32. And now we just create that body in our body vector. How bored are you? Speak up. Okay, I'll do my best. Right, so we've created our points. We've created our body to contain the points. And now we're going to I need to display it with OBS Studio. Going to refresh the page and see our newly compiled code. Oh, we've done a silly. we forgot to add a velocity field. So let's just make the velocity field 0 for now in both of the points. Now it's recompiling, and there's no errors this time. That's good, just a lot of warnings. So let's refresh. And as you can see, whoa, we have 2 points. That's good, that is progress. That means we're getting somewhere. So the next thing to do is to draw lines between joints. So we'll do that now. First of all, I'm going to make the size of the point a little smaller. Secondly, we're going to draw a line for each of the joints, and that code looks like this. Window, not winnow, draw ext, presumably meaning draw extension. I'm going to create a new line from which positions? Well, a pos.x, a pos.y, to b pos.x, b pos.y. And oh, that's correct. And now we're going to use a method on it called dot with thickness, and let's give it a thickness of 2.0, which is almost as thick as me. Next line, what colour do we want it? Let's give it a nice red colour. And then you need to add these bits at the end, just because. These are sort of all of the annoying bureaucratic bits that tell the program to do what you want it to do. 5. Why is there a 5 here in the example? Okay, I'll just roll with it. 5 is fine. 5 works for me. Right. Now I'm going to put the drawing of the points below, so they appear on top of the lines. Now hopefully this should work, and it doesn't because we have a bunch of errors. No field points on type mut world. Right, type mut world. There. That's because it's not self anymore. It is body. No method name draw ext. Oh, it's meant to be just x. And compiling. There we go. That's quite amazing. Right. And if we show OBS Studio, if we show our web browser, you can see that, oh look, we have no line, and there's a reason for that. We forgot to create a joint between them. So see how boring a lot of this code is? It is really quite boring. Let's create that joint. Body dot, yeah, can't spell today, joints dot push, and then it's going to be index 0, index 1, because those are the 2 points we want to join here, and then let's give it a desired length of 100. Not that that really matters yet. So let's see. Recompiled successfully and refresh the page, and there we have it. We have our line between points. Very cool, sort of. Right, I'm going to just smarten things up. Make the line a little thicker, make the points a little smaller. I've not enabled it on the viewer. There we go. You can see we have points and line. Very nice. Oh, it's worth mentioning that my stream viewer swaps red and blue colours for some reason. There we go, that's better. Right. Now I'm hoping this thing is going to constantly draw the call the draw function, but it might not. But if it does, we can use that to tick the world. So I want to call world.tick. No, self.world.tick. Nope, not even that. For body in self.bodies body.tick. Use that to tick all of the bodies. And now compiling. Yay, that's better. So, let's show the browser again. Let's see what happened. Whoa, that actually worked. As you can see, our code is sort of working. It's not perfect because there's no damping at the moment, but as you can see, we have a spring, effectively. A spring between 2 points. So, now let's do something a little more interesting and create a box. Woo, we've got to the so you can see we've finally created something very slightly interesting, sort of, and by some definitions you might find it really boring, but let's zoom out a bit so you can see this properly. A bit too small. There. Right, let's add 2 more points and create our box. Right, I'm going to create one at 128, 32, one at 32, 128. We're going to create 2 more joints, 3 more joints actually, so between 0 and 1, actually let's do this from, right, this is the top left one, this is now the top right one, this is the bottom left one, and this is the bottom right point. So we want a connection between top left and top right, so 0 and 1, we have that. Bottom left and bottom right, so 2 and 3, we have that. Now we want a connection between 0 and 2, which is top left and bottom left, 0 and 2, and a connection between 1 and 3, which is top right and bottom right. So that should work. So recompiling our code. Let's see what it does. This is a total pain having to re-enable the browser window every time. And we have a cube. It's not very interesting. It doesn't really look very interesting at the moment, but that's to be expected. We're about to make it extremely interesting. So, there's one last thing I want to do before continuing, and that is to add a cross joint on the diagonals. So that looks like 0 to 3 and 1 to 2. So let's just save that and give it a check, even though we already know that's going to have worked. There we go, we have a cross joint on the diagonals. It's very springy at the moment, so later on we're going to have to find a way to dampen that out through some springy mechanics or something like that. So now we're going to add some gravity. Gravity is very, very cool. because it totally changes things up and means we get some actually nice physics. So the way we're going to add gravity is in the point tick method. We're going to increase the velocity, specifically its y value, by a certain value. I'm going to go for I think about 0.5 to start off with. Now there's one last thing we need to do as well. We need to make it stop moving when it hits the bottom of the screen. So at the moment we're just going to hard code in the bottom of the screen, which was, as you can see below here, 600 pixels. So we're going to say if self.pos.y is larger than 600, because our coordinates start from the top and go down, because we do things in reading order. Self.pos.y is equal to 600 and self.vel.y is equal to 0. So what this does basically is says when the position of the point falls below the bottom of the screen, it's going to move itself back up to the bottom of the screen and set its y velocity to 0. Fairly intuitive. There's something else we're going to do as well though. Actually I'm going to do larger than equals there. There's something else we're going to do, which is we're going to give it some friction in the x-axis to make it slow down. This is really important because otherwise we get a shape that slides everywhere. So we're going to do that like so. Self.vel.x times equals 0.9, which means that every single frame this runs, the x velocity will be multiplied by 0.9, which means over time it slows down, or rather it gets smaller, its magnitude shrinks. So we are ready to go, but to make this bit a little bit fun, I want to make it do something cool, which is to flip over. And to do that I'm going to set the top left point's velocity to this. 5, 0. This should be quite fun, assuming everything works. Let's check everything compiled. Yep, it did. Are you ready for this? Make the default length of the diagonals longer. Yep, that is a very good point, Yido. So I should use Pythag for this. So a squared plus b squared equals c squared. So a and b are both 100. 100 squared is 10,000. Add them together, 20,000, and the square root of that, which is, let me just get a calculator because I'm not doing that in my head, 141.4. So let's round that to 141. Now it should be more balanced. Thanks for that observation, quite useful. So now let's recompile the thing. Recompiled, and now refresh. Wow, look at that. That looked very cool. Maybe it's just me, but I really love watching that. In just a few lines of code, and it may not be perfectly accurate, that is true. This definitely does not follow perfect Newtonian mechanics, but in just a few lines of relatively basic code, we've created something that behaves in an intuitive, physical way. Pretty cool, right? Oh wait, you didn't even see that. did you? Because I've not enabled that screen. That's a shame. Ruined the big reveal. Right, let's refresh. Here's what you get. And see that once more. That's very fun to watch. So, what things can we do now? Well, now the obvious thing to do is not anything sensible, but to build more points and see just how crazy we can go. So, of course, I'm going to do that. Let's build an extra cube or square on the side of it, this time at let's go for 250 across. Okay, now like before, I'm going to add some joints this time. Oh no, this ordering change messes things up, doesn't it? Actually no, it doesn't. I'm going to go from 1 to 4 and 3 to 5 and then 4 to 3 and 1 to 5. I'm going to make these a little bit to make these 122. Yeah, that's great. Oh, we need one more joint. 4 to 5. This looks a bit strange. I'm going to make these a little bit larger. Maybe about that. Okay, let's see what happens. Let's hope it doesn't crash. And compiled. Oh, you can even see me writing that code. Okay, well basically put, I've just added a bunch more points and a bunch more joints. Let's give it a look. See how badly it failed to work. Wow, that is fun to watch. So this is a pretty good first step on making something that's eventually going to evolve. How it's going to evolve, you might ask, or how is it going to evolve? Well, we're going to be making use of a fitness function, and also a way to determine which out of a population of creatures is the most adapted, and also a way for the creatures to evolve. So we'll find some way of allowing them to control themselves. Maybe we'll use a simple neural network or something similar to that, but now is probably not the time, because I am quite tired and I have an early morning tomorrow. But I'll put the code up on GitHub in a gist as before. You saw the instructions at the beginning of the video about how to set up Quicksilver, and I'll call it Darwin.rs. Now that's that's on my personal GitHub gist. Put the link in the chat, and I'll put the link on Discord. There we go. Hopefully that was enjoyable, a bit of fun, making jiggly, bouncy, weird physics things out of joints, totally bastardizing Newtonian mechanics. Yeah, I'm going to end the stream now. Thanks all for watching. See you later.